human beings were working on creating this geared and cogged machinery that reflected the patterns in the sky.
Oh, is that a recreation of it?
That's a recreation of something like it, yeah.
Around 60 before Common Era, a massive merchant ship was sailing through the narrow waters between Crete and the Peloponnese. As it approached the island of Aegila, an area once plagued by pirates, a violent storm hit. With no safe harbor nearby, the ship sank, taking at least 4 lives with it.
The entire facade of it is covered with writing that had never been seen previously.
This wasn't just any ship. It was about 40 meters long and loaded with valuable cargo. Its hold was packed with amphorae filled with wine, finely crafted goods, marble sculptures, bronze statues, and delicate glassware. But hidden among these treasures was something far more mysterious. A small wooden and metal device, covered in dials and gears. This wasn't a simple timepiece. It was a highly advanced instrument designed to track the movements of celestial bodies. Graham Hancock has recently shared a shocking perspective on this discovery, one that challenges everything we think we know. This is the story of the Antikythera mechanism.
It's an instrument of mathematical astronomy. It's intensely rich in mathematics. It's not complicated mathematics, it's simple arithmetic and it's simple geometry, but put together in an absolutely beautiful way.
As a child, I learnt about the mechanism and I was absolutely fascinated by it. And I often wondered how researchers, scientists ever got to work on something so remarkable.
Discovery and early excavation. In 1900, a group of sponge divers from the island of Symi stumbled upon an ancient shipwreck near Antikythera, an island once known as Aegila. One of the divers, Elias Lekopantes, descended about 40 meters and surfaced in shock, claiming he had seen lifeless, naked bodies scattered across the seafloor. When their captain, Demetrios Kontos, dove down to investigate, he realized that what they had mistaken for bodies were actually marble and bronze statues. To prove it to his crew, he brought up a full-sized bronze arm. Before long, the divers teamed up with the Greek government and archaeologist Georgios Oikonomos to explore the site in more detail. This effort became the world's first underwater excavation. As they worked, they uncovered a wealth of artifacts: bronze sculptures, amphorae from Rhodes, marble statues from the Aegean, glassware likely from Syria, Palestine, or Egypt, and a collection of silver and bronze coins from cities like Ephesus and Sicily. The coins, dated between 76 and 67 before Common Era, suggest that the ship went down sometime within that period. The variety of items on board has led to speculation about the ship's purpose. Some believe it was a merchant vessel bound for Rome, while others think it may have been carrying looted treasures. Among the nearly 100 marble and bronze statues recovered, one stood out: the Antikythera Youth, a striking 4th century before Common Era sculpture that quickly captivated the public's imagination. The excitement over these discoveries took a turn when a telegram reported the recovery of a slab with an unreadable inscription. At the time, no one could have imagined that this corroded piece of wood and metal would later be identified as the world's first analog computer. Initially overlooked in favor of larger, more visually striking artifacts, the slab was damaged when it was pulled from the seabed. By May 1902, the slab, now known as the Antikythera mechanism, had broken in two. Accounts vary on how this happened, but archaeologist Valerios Steas noticed something remarkable: a metal gear and Greek inscriptions hidden within the fractured piece. This small discovery sparked over a century of research into the artifact's true purpose. Reconstruction and analysis. When experts first attempted to clean and preserve the mechanism, they separated the slab into 3 main pieces. Today, it exists in over 82 fragments. 4 of these contain gears, while many others have inscriptions in ancient Greek. The largest gear measures just 13 centimeters across and originally had 233 teeth, showing an impressive level of craftsmanship. Early translations of the inscriptions included the phrase "ray of the sun." Some researchers saw this as evidence that the device was an astronomical clock. Others were skeptical, believing such technology shouldn't have existed until much later. As more details emerged, inscriptions provided additional clues. One mentioned an Egyptian month, suggesting a solar calendar, while another referred to Venus as Aphrodite, hinting at a connection to the moon's cycles. By the 1930s, scholars theorized that the device might have functioned as an astrolabe, or planetarium, tracking the sun, the moon, and the 5 planets known at the time. Work on the device came to a halt until after World War II. British physicist and science historian Derek de Solla Price took an interest in it and noticed that much of the mechanism had corroded into fragments. He proposed that the device was designed to calculate time cycles and astronomical events rather than serve as a navigation tool. It was likely just being transported by ship to its owner. Price's research took a big step forward in 1971 when nuclear physicist Charalambos Karakalos used X-ray imaging to reveal 30 gears hidden within the fragments. Price attempted to reconstruct the device, and while his version didn't perfectly match the precise gear shapes, it was an important early attempt. In the late 1980s and early 1990s, researchers Michael T. Wright and Al Bromley used linear tomography to examine the device in greater detail. The most advanced studies, however, began in 2005 through the Antikythera Mechanism Research Project in collaboration with the National Archaeological Museum. Using CT scanning and reflectance transformation imaging (RTI), researchers were able to reveal intricate surface details. CT scans were especially useful in exposing the internal structure of the fragments, even uncovering hidden inscriptions that shed more light on how the device worked. So far, researchers have transcribed around 3,000 of the estimated 15,000 characters on the Antikythera mechanism. They now believe that about 30% of the original device has been recovered. Thanks to advanced imaging studies, we have a much clearer picture of what this ancient machine was designed to do. At its core, the Antikythera mechanism functioned as an early analog computer, built to track astronomical movements. If you're looking for a modern comparison, think of a mechanical wristwatch. Except instead of just telling time, this device calculated the positions of celestial bodies. Design and function. The mechanism was a small, box-like device about the size of a thick book, measuring around 30 centimeters tall, 20 centimeters wide, and 10 centimeters deep. It was housed in a wooden case, with its front and back covered by rectangular bronze plates. A knob on the side allowed the user to turn the internal gears. On the front, a circular dial was surrounded by 2 rings with different markings. The inner ring was fixed and divided into 12 sections, each representing a zodiac sign. Each section contained 30 evenly spaced markings, reflecting the Babylonian system that divided the sun's yearly path, known as the ecliptic, into equal portions. This setup allowed the device to predict eclipses using the Babylonians' Saros cycle, which spanned 223 lunar months, or a little over 18 years. The outer ring, which could be removed and rotated, displayed the Egyptian calendar in Greek letters. This calendar had 12 months of 30 days each, plus 5 extra days at the end of the year. Since the Egyptians didn't account for leap years, their calendar slowly drifted out of sync with the zodiac over time. The ability to adjust this ring helped correct that shift. The front dial of the device provided even more details. One of its pointers showed the moon's position and phase. Attached to it was a small sphere, half black and half white, mimicking how the moon's appearance changes throughout its cycle. The mechanism even incorporated epicyclic gearing to account for the moon's varying speed along its elliptical orbit, marking the first known use of such technology. Another pointer tracked the sun's movement along the ecliptic, possibly indicating the day of the year and even marking the paths of the 5 planets known at the time: Mercury, Venus, Mars, Jupiter, and Saturn. On the back, 5 separate dials displayed different types of information. 2 large spirals featured engraved scales and radial markings, while 3 smaller circular dials had tiny pointers. The top spiral, called the Metonic dial, was divided into 235 sections, each representing a lunar month and labeled with the months used in Corinth. This aligned with the 19-year Metonic cycle, where lunar phases repeat on the same days. The device also accounted for the 76-year Calippic cycle, an extension of the Metonic cycle that helped align lunar and solar years. Another spiral at the bottom was used to predict eclipses and track the current month. To reset it, users had to manually lift a pin and move the pointer back to the start once it reached the end of the spiral. One unique feature on the back was the games dial. This dial, moving counterclockwise unlike the others, calculated the dates for major Panhellenic athletic contests such as the Olympics, Isthmian, Nemean, and Pythian Games. It also set dates for smaller events like the Games of Na and the Games of Aleia of Rhodes. Small Greek inscriptions were carved around these dials on the bronze, filling every available space. Additional text was engraved on the front and back covers, acting like instructions or a manual for the device. More than 50 lines of text remain visible on the back cover, providing a systematic overview of the dials. In its current state, the Antikythera mechanism is believed to consist of 69 gears working in concert to drive the various dials, although some experts suspect that the original device might have included even more components. Purpose and historical role. This mechanism functioned as an astronomical calculator that allowed users to select a date from its calendars and then view the positions of the planets, the moon's path and phases, and the cycle of eclipses. When first recovered from the shipwreck, some believed it to be a tool for navigation. However, another idea is that it was intended for teaching or demonstration, rather than for practical navigation. Professional astronomers of the time would have required instruments capable of measuring fractions of days and the changing lengths of daylight and night. In contrast, the device seems more suited for educating philosophy students and elite members of society about celestial events and their possible effects on life. Its small size suggests that it was designed for one-on-one lessons or small group sessions rather than for use in large public forums. Its complex design indicates that it was meant for specialized instruction rather than for everyday use. The survival of the Antikythera. Mechanism also offers a glimpse into the craftsmanship of the ancient world. Although gears were known to the Greeks, this device exhibits a level of detail and precision that was not expected for its time. The gears were carefully cut from bronze sheets to reduce friction, and the mechanism survived while many similar bronze and copper objects were melted down and reused. It is possible that other similar devices existed, including earlier models or even more advanced versions. However, because metal was precious, many such artifacts were likely recycled. The Antikythera mechanism may have been built using metal reclaimed from an earlier device. In the 1st century BCE, Cicero mentioned 2 machines built by Archimedes in the 3rd century BCE and another by Posidonius in the 1st century BCE. These devices, described as celestial globes, were capable of reproducing the motions of eclipses and the planets. The Greeks and Romans had a clear grasp of the moon's variable orbit and the use of predictive gear systems. Yet, Before the discovery of the Antikythera mechanism, there was no concrete example of what such a device might look like. The existence of this device confirms that, although rare, such constructions were known and possibly produced multiple times in history. However, their creation would have required thousands of labor hours and significant expense, which implies they were not made on a large scale. Archimedes is often credited with setting the stage for analog celestial computing. The Antikythera mechanism was built sometime after Archimedes' death in 212 BCE during the Battle of Syracuse, likely by a student or follower familiar with his work. It is probable that the inventor worked with skilled bronze smiths and other craftspeople, making the creation of this device a group project. Early measurements and an inscription mentioning the Corinthian month led some to believe that the mechanism was intended for someone from the Corinthian colony of Syracuse. However, further studies suggest that its origins might be traced to Epirus in northwest Greece. This route is consistent with a ship heading toward Rome, particularly since one of the dials refers to Pan-Hellenic games. One of these games took place in Rhodes, far from Epirus, which has led to another theory. Some rulers of Epirus had ties to Rhodes, and the astronomer Hipparchus, active in the mid-2nd century BCE, was based there. The device's incorporation of Hipparchus's ideas about the moon's movement supports this connection. Ultimately, as often happens in archaeology, the exact origin of the device remains a mystery. It is also possible that the mechanism was simply being transported to Rome, where Greek artifacts were in high demand. Wealthy Romans of the time collected such items to display in their homes. The dating of the Antikythera mechanism has long been debated. Since it functioned as a set of calendars, it required a starting date to calibrate the motion of the planets accurately. Some scholars have pointed to eclipses around 204 BCE as a reference, while others, in 2022, suggested that the calibration date was December 23, 178 BCE. These dates refer to calibration rather than construction, but they provide insight into when the mechanism might have been built, possibly slightly earlier or later, depending on the recorded eclipses. Graham Hancock's perspective. Graham Hancock and Joe Rogan talked about the Antikythera mechanism, an ancient Greek device that many consider the world's first analog computer. Hancock pointed out that it proves the existence of a lost navigational skill that historians haven't fully accounted for. The mechanism, discovered in a shipwreck, is a complex system of gears designed to track planetary movements and measure time. Its level of sophistication suggests that the ancient Greeks had a far greater understanding of astronomy and mechanics than most people realize. Hancock believes this kind of technology didn't just appear out of nowhere. He suggested that Greek navigators and ship owners may have kept it a closely guarded secret, similar to how governments today protect classified technology. The fact that so few of these devices have been found raises questions about how widely they were used and where they really came from. Rogan and Hancock agreed that discoveries like this challenge what we think we know about ancient civilizations. If the Greeks had such advanced devices, what else might have been lost to history? Hancock's main argument is that we're only looking at the surface of human history while an even deeper story remains untold. A window into ancient science. The existence of the Antikythera mechanism shows that the Greeks had a more advanced understanding of astronomy than many had assumed. Their grasp of celestial cycles was comparable to scientific methods developed much later. Experts studying the device have acknowledged that its level of technological detail is hard to believe for its era, yet it clearly belongs to the Hellenistic period. The Greeks nearly invented clockwork centuries before it became common in later history. Unfortunately, due to a lack of documentation and the rarity of other similar devices, the potential of this technology was never widely recognized. Had it been more common, it might have accelerated scientific progress by many years. As Arthur C. Clarke once remarked about Greek insights, it is possible that if their ideas had matched their skills, our exploration of space might have taken a very different course. While human space travel to distant stars remains out of reach, the Greeks and Romans managed to bring the cosmos closer to their everyday lives through devices like this. Beyond its technical details, the Antikythera mechanism represents a deep curiosity about the skies and a wish to understand the regularity of celestial events. Ancient Greek culture connected these events not only with practical activities such as sea travel, but also with philosophical and religious meanings. The stars, planets, and the phases of the moon were often linked to myths and were influential in shaping cultural rituals and social organization. The mechanism, with its precise calculations, likely served both as an educational aid and as a symbol of the connection between science and belief. Although the device emerged from Hellenistic Greece, it is clear that this type of scientific inquiry was not isolated. The Greeks were part of a wider Mediterranean exchange of ideas, where innovations were shared and improved. The complexity of the mechanism points to ongoing advances in mathematics and astronomy that may have been influenced by earlier civilizations such as the Babylonians, Egyptians, and Mesopotamians. The combination of these traditions in the mechanism highlights how ancient cultures influenced one another in the realm of intellectual discovery. The rediscovery of the Antikythera mechanism in the early 20th century opened a window into a period of ancient engineering and learning that had long been forgotten. Its true importance came to light only when modern imaging techniques made it possible to study the corroded remains in detail. X-ray imaging and other methods revealed the inner workings of the device and deepened our appreciation of ancient technology. These findings have renewed interest in the scientific achievements of the past, reminding us that even in ancient times, there was a strong commitment to understanding the world. In many respects, the Antikythera mechanism serves as an early example of technology that predicted events, an idea that would later influence the development of computing and mechanical devices. The work done by ancient Greek scientists on devices such as this laid the groundwork for centuries of scientific progress. Their achievements, impressive given the limitations of their era, continue to spark the interest of modern scholars, engineers, and historians. Thank you for taking the time to learn about this fascinating artifact. If you enjoyed this exploration of the Antikythera mechanism, please show your support by liking and subscribing to our channel.